Okay, I think yeah. Okay, hello everyone. I think I should do some introduction. Uh, Perhaps some of you didn't know me. My name is Jian Hao. Okay, okay, and as displayed in the Zoom up. Okay, my surname is Laila. Okay, and I will be covering actually the three lectures. But one of the lecture relativity is covered is replaced by others. So I will cover only two lectures. One is for fluids and one is for rotational system in the last lecture. Okay, okay, so I'm from USM. In case you someone didn't know, USM stands for University Science Malaysia. Okay, so university from Malaysia. Okay, so it's in Penang. You want to say hi to me when you are in Penang also can. Okay, so I'm from USM. I'm studying pure physics. Currently is third year. Third year. Okay. So we are starting. My track is a pure physics. So in case you have anything you want to ask about university stuff, uh, in Malaysia, especially, yeah, you can ask me also. You want to test me through Discord or through my WhatsApp number or something. Okay. So yeah, this about my um self introduction. Okay. So it's more about me, and I don't know about you guys much. I know some of you are, but yeah, just maybe we can meet physically during the camp. Next time you can go. Okay. So this one yes, I should proceed to some disclaimer. Okay, some disclaimer. Okay. Okay. Anything that because I still quite fresh okay, because I am ex Olympiad also, and uh now I'm doing some quantum field theory stuff in my FIP. So I'm much touched on the things like quantum stuff, uh, and honestly say much of the things that I learned in my PSY is still some of it is still remember, but most of them is like forgot or I forgot most of them. So if you found that I have many I have some mistake that I spoken in the lecture, so please correct me. Okay. I don't want to like deliver the wrong knowledge. So yeah, just like we learn together also. So this time there's like I trying to recall back when I preparing the lectures. And actually this not is prepared by Zhi Zheng. And yeah, about the first stuff. So this will be covered in this today stuff. And some yeah, this is first of all disclaimer, and anything that you are not clear and you want to discuss with me, like you want to debate with me, you feel free to do so. You want to open your mind, you want to check, also can. But then I'm for myself is the person that more towards want to prepare all the things on, and I'm not the real time. It's like my brain is not very fast. So uh, there's a maybe I need some time to go through it and want to reply your questions in a correct way. Okay, maybe you give me some time to think about it, and maybe you want to reply you after lectures or after some time. Okay. Okay, so it's just a two disclaimer lah. So you want to anything you want to any question you want to ask, anything that you have found is not correct, yes, spoken for me. Okay. Okay, so we learn together. Okay. Um, set 04. Okay, hope everything is clear now. Okay. Okay, without further ado, I think we can start with the lecture. Okay. Yeah. Okay. Okay. So what we are seeing today is about fluids. So I basically want to start with the easier things when we want to further sorry, I mean,
Check the baby, okay?
sorry, I mute your mic. Okay, so um, yeah, we want to. Basically I will start with the simple stuff first. What we want to go through and giving some big picture we want to cover today. So today we're talking about the something that we can grow water or grow the air, and yeah, this basically you want to know that what is the fruits. What is a fruit? Okay, anything you can anyone can answer me what is a fruit, and any kind of definition that you are thinking of, anything you think of that is related to fruit, you can type in the chat box. It's like I don't know I don't know anything that, so I asking you guys like what is the fruit? What do you think on the plus? Okay, so yeah. Well, the plus is some of the fruits and then just I mentioned just some the water or the air stuff. Yeah, just no definition. Yeah. Whereas you see in solid have the lattice structure and have a definite shape. And in the fluids, you can use the container. Let's say you use a container to fill some of the water, and there is a shape of the water, um, shaped by the container. Like, and for example, you fill the air, fill the container with the A, and there is a shape of the A. Yeah, there is a no definite shape. So in case there's a discrete difference is like fluids and also solid. So yeah, this we want to study the things that we want to talk about the fluids, and we'll go through some of it, and the questions will the question I will just briefly touch about the idea, and the question I may not touch on it. So depends on the time depends on the time that we end about it after sure after giving some ideas. So we are talking about some fluid statics, and which is by terms you know that it's the things that are not moving. Fluid dynamics, the things that are moving, and fluid dynamics, and some of the um because the static stuff, and we are not talking about the reality stuff. And when we want to go into the reality, there is a viscosity, which is at the first we assume that there's no viscosity. When we're talking about the statics. Sorry, the what's that? Fluid dynamics. Yeah, fluid dynamics. They assume that it's not no viscosity, and after this and we'll hear about some real stuff, which is air resistance, some kind of the air resistance. Okay, some kind of the drag force, sorry, some kind of the air drag force, and can be the air resistant and can be the resistant water also. Is viscosity, about the viscosity, drag force. And we are talking about the surface tension and pressure that you might see in the every days in the real life. And some of the equation and thermodynamic stuff, thermodynamic physics. And we'll go back again like kinetic theory and some of the fusion and effusion. Yeah. This basically we want to talk about this all things to things. Okay. Uh, yeah. And we start with the ideas that the things that didn't move. Okay. Because the things that didn't move is much more simple than the things that moving, because you are accelerating as you are the things that you are have the velocity is moving. Sometimes you if you experience some air resistance, there's more complicated, and there's some if there is a static, and when there is statics, the idea is that it can be the equilibrium, and we can use the Newton second law. Let's say we have the in this context, we're using like Newton second law equal to zero to study about a fluid for one object. Okay, let's say we have an object. This one object, um, it's like it's like a object have a cross-sectional area A, and with some dy, height of dy. Okay, so it's a small height. Okay, we want to study about this when it's immersed in the water, let's say, or in a fluid, okay, in the water. Okay, so we want to do some draw some force on it. We know that they're in which is and the objects in the fluid. Okay, the water will exert the forces on the object. Okay, so let's say we have a that the forces that we are saying that we want to, because we want to say about the fluid, so we define things that, okay, it's called a pressure. It's some kind of something that related to a force, and we want to analyze one a bit. Okay, so let's say we have a pressure exert on the exert on the below of the surface of the object, and also another forces exert on the top of the object. Sorry. Okay, so this will be the two forces. Sorry, two pressure. Okay, which is related to some forces. Okay, and because we are in Earth, right, yeah, just we were experiencing some gravitational pull, and we should know that there's a weight on it. Okay, so when we talking about these three forces, okay, because it's in set equilibrium, so we can simply add up. It depends on the direction, upward or downwards. Outward, Upwards is a positive direction, and downward is a negative direction. So we'll get on this, and notice that this is a function of p. Okay, y plus dy. Okay, so don't confuse that it's a thing, this thing multiplied with this thing. So just a function of p with y plus dy, and function of p y. Okay, so we want to so we try to multiply on it. This will be the forces. Okay, of the forces like y plus dy. This thing, this will be the forces. Forces, and this will be our W. Okay, W is equal to mg, right? Mg is always below a dy. So it's just a density times of volume. Okay, so I think this things are interesting. I think this thing you guys know. Uh, and we want to get this fraction, and this one is what this. Let's say with this one is a approach to zero. We take the limit, so it become a calculus and differentiation now. Okay, so we get this. Okay, and this will be our equation for when the object is static in the fluid. Okay, so which is in equilibrium. Okay, so and another things that we want to knowing about, I think another things that we want to talk about is the Pascal principle. Is something is talking about you are, let's say you press you have two things, just a simple example, two open, so open tube. When you press some force on the fluid, and based on the definition of the let's say with this fluid is not incompressible. Okay, which means that it cannot compress enough. Okay, so there will be another forces will be added. This another open tube. Okay, so means that when you have a increase of pressure in on the fluid, and throughout the entire fluid, there will be the increase of the pressure throughout the fluid. So let's say you have the guys here, you're experiencing the pressure also. So yeah, and this is called the Pascal's principle. Okay, and Archimedes in and there's important uh, and there's the things we learned from high school, the three principle. Sorry, some and another principle is about the Archimedes principle. Archimedes principle, if you check on the history, right? Some fun fact about it. I give some. Okay, so I can copy on this. uh, I will just share the link into the chat. If you save it, then save it. Just some fun fact stuff outside of the physics. Some it's yeah, still inside of the physics, subset of the physics. Uh, in the set in the set of just some historic stuff. When you are talking about Archimedes principle, you think of some guy that bath in the this what's it called? Bath in the- and he immersed inside in the water, and the water flow out that and the amount of the water flow out, okay, you found that it can measure the measure, is it the real goal, is it measure the goal, is it the real. Okay, so some, I think you heard about this some of the history, right? But in fact there's a history about real history about the Archimedes principle. Is talking about some war stuff and the ship stuff. You can check on it. Okay, so then go back to the lecture. So um, the things that I want to talk about is the Archimedes principle is based on have two important things. Okay, so so an object in the fluid, right, you will have your experiencing the same magnitude as the weight of the fluid displaced. Okay, so wait, okay. Given that the object is given the sorry, okay, given the object is fluid, uh, the fluid flow, flow, flow in the fluid lah. So we'll experience a same magnitude as the buoyancy force will same magnitude as the weight of the fluid displaced. Okay. So another thing is act on the center of gravity lah. Okay. Okay. And the other idea when we talking about the fluids is the other ideas that we're talking about the fluids is the fluids will tends to change the shape. Let's say you have a water droplet is uh not experiencing any gravity. In another term is fluids don't have you put a fluid uh, in a space that don't have gravity uh, gravity add on it. Okay, so the fluids will tends to channel straight their minimum potential energy. Why? Is it why? Maybe you think of why is it so minimum potential energy? If you're talking about the two things, it's a more the shape that minimum potential energy is more stable lah. And you found that in another fields, another basically it's in another physics field lah. So we have found that is if you find that it's the things prefer the minimum potential energy. And maybe one of the question may arise, how about uh the nature is we learn from thermodynamics. Nature is thermodynamics second law. Nature tends towards there's something about entropy, right? Nature tends towards a bigger entropy. Then how we can react the minimum potential energy with the entropy with we learn in the second law of thermodynamics. You can check on this. If nothing. Okay. It's another thing you can check it out. So why is it how is it the two things? So we want to get some idea that we learn from thermodynamics and want to apply it and also in the idea that we learned just. Okay, so uh, yeah, this will be the idea of it. Another things we want to talk about is question you can try 1.3, 1.4, 1.5 home at the home. So there's more question you can try, but this is suggested by Zhi Zheng. These three questions you can try at the home. Must try. Yeah. And if you have any question, you can try to you can mm, anything you want to discuss, you can ask me or Zhi Zheng. Either one of me or either one of us. Okay. So and that's the thing about the static static things. Okay. Next one we want to talk about the dynamic things. Good dynamic. Okay. Change. By the way, you have anything that you are not sure, you can try. You can just write in the chat box. Because I sometimes my English is not for now it's not exact, not good. So if you anything like not sure, you can just type in the chat. Yeah, sorry for that. Okay. Okay. So the second thing we want to talk about is fluid dynamics. Fluid dynamics and get the things that we want to talk about the streamline. Streamline. Let's say we have the fluid, like okay, fluid. Use a tube. There's a tube, and let's say the fluid is moving. Okay, generally the fluid is moving in that direction. Okay, let's say we have one particle. We have one particle is not moving in this velocity. And let's say it's velocity one, and after some time it's moving until here with the velocity two. Okay, so you think that fluid we have many particles, different particles. Okay, let's say many particles have its own velocity. Okay, have own velocity, and there is a field of that field of the velocity. Okay, a field of the velocity we can talk about it. So let's say we have the that kind of velocity. Okay, a particle that moving from here until here. Okay, so we can draw a line. Let's say it's a line that particle is moving from here to here. Okay, so and the line is basically is tangent to the particle velocity of vector. Okay, that's what I wrote here. Okay, so you'll find that at this point, let's say you want to at this point the particle, the line is like this, and the uh, tangential of it, tangent line of it is the velocity. Okay, so basically this is a streamline. Okay, the streamline, and the collection of the string line is a string tube. We call that it's like a tube like. Okay, it's called a string tube. Okay, so with this in mind, with this in mind, and want to move on to some things and move on to something that we can do on something on the fluid dynamics. Okay, and this time is like okay, it's a trajectory found it's a trajectory is for fluid molecule when the flow is steady. Okay, and yeah, and from the conservation of mass, like let's say we have a particle, a masses of this of the masses, conservation of mass, and this will be the conservation from the conservation of mass. Then we can define one of the things, the masses from move from one side to another side. So we can define is conservation of mass, and it's the continuous one. Let's say the mass won't be disappear or won't be like some suddenly appear out because of the reaction of the uh, virtual particle and the particle. So yeah, it doesn't mean it doesn't want things like that. It's more complicated, and we want to say something of the conservation of mass. The mass from here and to here is the same methods that moving. It's not compressible also. Okay, it's constant, so we define thing is dn over dt, okay, with the low AV. So, and we learn about the steady fluid, and steady fluid non-viscous, which is don't have the drag forces when the fluid is moving in the tube, let's say. And also incompressible, we have the things that we know that is about the Bernoulli principle. Maybe we heard that Bernoulli principle is something about like we have a things ball, or let's say we have the block. Let's say this flow of the fluid is faster, and let's say this one, the flow of the fluid is slower. Okay. So when the thing is moved fast, when the fluid is faster, this is a lower pressure, and we heard about this thing like the higher
Oh
velocity
my
of the
god,
fluid
it's okay with
is a
this.
lower pressure. It's, okay. So yeah, there will be the Bernoulli principle that we heard before, and we want to apply some. We want to know that there is a quick question of that, and we call it a Bernoulli equation. And if you want to know how is it derived from, you can start with the conservation of energy, or you can try from the Newton's second law. Also, there's another way to try. You can try to check. And conservation of energy, you can basically is about the when the increasing of the total decrease in pressure will be the let's say we have the pressure energy, and a decrease in it will increase of the mechanical energy. So the total energy of the system is constant. So we can try to apply this conservation of energy and found that this equation. Okay. The difference of these things is equal to zero. Let's say this means that this one P plus 1 over rho v square rho gy is constant. Okay. And another fact that you maybe you notice that is the want to separate out into three things. This should be we call a pressure energy and a kinetic energy, potential energy, some kind of okay. So you want to some kind of like energy. And another thing we can say that is static pressure also, and the thing that static they act on it, a static pressure and dynamic pressure and hydrostatic pressure. Okay, and there's there's some there's some things that you might need to take note when you are applying the Bernoulli principle. Uh, One thing is three things. One is a steady, non-viscous, incompressible flow. Okay, and also it's along a streamline. So you want to know. Yeah, in real life, right? In real life, if you want to talking about a tube with a fluid, a tube again. Okay, so in real life, the fluid is moving. Let's say I use carbon. Will move like this. In real life, in reality, there is the viscosity in the fluid, and let's say it's a fluid is touching the surface of the tube, and there will be the drag forces will somehow make that point of the fluid is not moving. So we'll see that the on what is that called? And actually, if you want to draw a velocity some kind of velocity path, let's say the this will be the velocity trajectory. Okay. In the existence of the viscosity. Okay. But in these cases, Bernoulli principle, we're talking about is no viscosity, which means that we can be analog like we are considering a big tube, okay, a big tube, and we're considering a middle fluid, okay, because if you draw this in whereas it indicate the amount of the velocity of the fluid moving from left side to right side. Okay, you found that this changes, like if you draw a tangent line here, and also tangent line here, here and here. Okay, you will found that in the middle side, the fluid is more hence is more steady. Okay, so in that side is the velocity. If you're considering the side is nearer to the tube, the um the fluid is not steady, and the velocity of this, let's say these two uh, fluid, these two particles, okay, it's not the same. Okay, so you cannot apply the Bernoulli principle studying about the side of the fluid they are nearer to the tube. Let's say in the real cases. But then in the question, so also we'll mention about is you want to consider principles also. So there will be the things you want to know about for the Bernoulli principle you want to think about. Okay. So for the bigger tube, the middle. Okay. So the idea is that for the bigger tube, and for the fluid, there is the middle nearer to the middle. So our middle is not near to the side. You'll have a steady flow of the fluid. You can try the example of this. And some of the questions, I think I will post it again with the questions that you can find out. 2.2, 2.5. Turbulence. Okay, turbulence is another thing that I want to think of. Then want to hand out on is about the chaotic motion. Chaotic things are it's the things that we have to analyze. When the things is like become a chaotic, and like a three body system is a chaotic motion that we have to analyze. Okay, so it's something is about the appearance also. We want to check out what is that appearance. And 2.9, 11, 12. Okay, so I want to read out a bit. Read out a bit is we talking about the fluid statics of Archimedes principle of principle. So the fluid tends to more stable shape, which is the more stable shape, which means there is the more potential energy. Sorry, minimum potential energy. And fluid dynamics, I want to talk about the streamlines of the Bernoulli principle, and want to take note on the condition that we can use the Bernoulli equation. More or less would be any question that you want to go far now. You're okay. Okay. Okay, so we'll go. That's one will be talking some real stuff. Okay, thanks. Talking some real stuff, and we want to analyze because the physics you want. If the one fact is that if physics is not uh close to the reality, and we want to imagine a cow become a point and something like that. So I want to approximate some stuff, and this will be not close to the reality, and something that physics in physics in high school is like want to approximate this stuff. Okay, no as A or no, assuming that this ball is a point, okay, and assuming that the earth is a point from far away. But then yeah, just I want to uh and we want to consider some real stuff. become more complicated. And the things that we want to talk now is about the viscosity. Viscosity is something about related to drag forces, drag force. And we know there is a drag force in can say we have a air resistance. Okay. Considering we have a boundary plate, let's say it's a solid, this one is a solid. And the thing, and I thought about when the fluid is moving towards the right side and have a contact on the lead plate. There's a contact on a solid. Okay, this will be a conditions that we say there is a no slip condition. Okay, so basically the fluid is in a zero velocity. Okay, so basically it's not moving. So it is have a and we can consider different. Let's say we consider this a fluid one chunk of weight, another chunk of weight, another chunk of weight. Okay, so let's say we have these two things is these two lines are moving with the different velocity. Let's say it's first the upper one is moving faster velocity. Okay, with the longer longer velocity vector, longer length of the velocity vector. Okay, so let's say it's moving faster. So if you the two when the fluid is moving in different velocity, right? And this will be shear stress. Some kind of stress is appear in that two different velocity of the fluids. Okay, two fluids with different velocity. Okay, so it will be the drag forces or the resistance when you are when the fluid is moving. Okay, so and we can define a force forces. Okay, we define a force as the drag force in the eta, okay, eta A dV over dy. Okay, and eta is called viscosity. Okay, viscosity of the oh that is internal pressure of the fluids. Okay, and we want to say this stress, shear stress. Stress is like some kind of things about pressure. It's something related to pressure. So pressure and stress. So pressure, the definition of pressure is FOA. So it's like write this out, and we can write it to shear stress equal to FOA and equal to this stuff. Okay, so if moving in this side, it will be to the equation that we have defined just now. Okay, next you can try at 2.13 and 14, 20 minutes. Okay, so there will be the drag forces. Okay, surface tension, things that you want to I want to focus on is like why it will be why have we have the surface tension on the on this stuff. Let's say we have the container with a fluid, okay, with a water, and you put a needle on the you carefully put a needle on the top of the surface of the fluid, and you found that the needle is some kind of rod. Okay, but then it's not rod because you know that the density of the needle is higher than the density of the fluids, let's say the water. So it should be moving downwards, but then it's fluid somehow it's rod. Okay, so what is that actually? Actually, this will be the surface tension on the top of the surface. Okay, if you want to analyze it molecularly in a small things. Okay, let's say we have the different particles. Let's say we know that in let's say we will consider H2O, the stuff that we are drinking all days, every day, sorry, every day. And let's say we have two water molecule. Okay, we consider it's a point. Okay, you know there's it's a three atom in. But then consider it's a point. Let's say we have the three different molecule. Okay, we will know that the molecule, the two molecules will attract each other. Okay, will attract each other with some energy, binding energy. Let's say it's a negative E. Okay, so in the in below the surface, the molecules attract each other in all directions. Let's say we consider this one molecule is attracted by other molecules in any direction. Okay, so you see that it draw with some many errors. And another things you want to consider is like surface by surface tension. Okay, so we consider another air water molecule on the surface, and you'll notice that the upper side is not don't have the water, and only the intermolecular forces. The molecular forces the attract uh in the is from the downwards direction, from the from the molecule below it. Okay, molecules below it. So you'll see that they'll attract by the molecule below it. Okay, so because it's you know that if for the for the molecule is below the surface you attract by the others molecule and balance. Okay, and balance in all directions. So the net forces is like uh is smaller. And if you think that the surface of the molecule on the surface is bind closer to each other because it's not balancing by the upper surface, upper things on the things upper surface. So you bind towards each other, and you see that there will be the tension on it. And yeah, and this basically is have the energy of the negative E over 2. Okay, so let's say you have the um this kind of energy, and there will be additional plus energy which is called that is a surface energy uh for the surface of the molecule they are binding towards each other. It is more closer, so have a tension on it. And somehow it's like the somehow it suggests that it's the more surface area, right? The more surface area, the more particle is binding toward each other. And the more surface area is more energy. So we define the things that we call surface tension. Okay, what is this things? Okay, if you do some dimensional analysis, if you see that it's energy. Energy is in the dimension of the okay. And this one will be the area. So it's L squared. So it just cancel it out. So it will be something about the force over length. Okay, so this will be the surface tension that we are talking about. It's something related to school. And so keep this in mind. We'll define the things we are talking about after this. We're talking about the capillary action and how we can use this surface tension to study some fundamentals. Okay, so we are talking about the fluid tends to the shape that have minimum potential energy. So in case you want to check it out, why and actually it's a sphere. Okay, why is this so? Uh, okay, you can check it out on the experimental proving by Swan. So there'll be some experimental proving is the when no gravity, like zero gravity, like the water droplet it tends to a spherical shape. Okay, so will be the minimum surface area and minimum energy. Okay, so there will be the things that we're talking about the Young Laplace equation. Things you'll be using also this Young Laplace equation. And notice that actually we are talking about the surface tension between the interface of the liquid and also the vapor. Or we somehow we can or sometimes we call it vacuum. It's not nothing. It's nothing on it. Okay. Classically nothing on it. Okay. So this is the interface that we are talking about. It's like VL. Okay. So we are talking about surface tension of the two liquid and vapor interface. Yeah, actually, this okay. This is the thing. LV. Okay. If you are moving on, we are talking about three interface. Okay. Solid, liquid, and vapor. Somehow we can call it vacuum. So okay. Three interface. And if you notice, you're doing some analog things and risking some. So, we skip we skip some details here. So we are just using treat the surface tension as a force, and we try to balance it out. Somehow we see that this three is a forces we are talking about. SL is a solid between a solid and liquid. Solid liquid interface, liquid vapor interface, and solid vapor interface. Okay, so the three forces can be balanced by using this. Okay. So and let's say it's a static thing. So it's the fluid is not moving. So it's is equilibrium and sustained by the surface tension. Okay, you will get the angle of theta in related to these three variables. We call it a Young equation. Young equation. Okay, don't mess it up with the Young modulus equation. These are the things in equation. And if you want to derive from the point of view of work done, three as a force. Okay, so this will be when this in equilibrium, the work done will be cancelled out, and you will get the same relationship. And notice that you want to analyze this equation. Okay. Okay, let's say this cos theta, right? Cos theta, we treat it to two situations. This is first situation and this is the second situation. Okay, A and B and B. Okay, the angle is below 90 degrees. Okay, so 0 to 90. Okay. So the cos theta of it is positive. And this one will be, let's say, will be an angle with smaller than 90 degrees, but lower than more than 90 degrees, but lower than the 180 degrees. So it will be the cos theta of it is negative. Okay. So so we consider these three constants as a positive values, and we notice that if we have the positive sign in the cos theta, and let's say this equation gamma SV will be greater than gamma SF for positive situation, and for the negative equation, negative situation, it will be another way around. Okay, and we define these two situations will be hydrophilic and so hydrophobic. Maybe hydrophilic and hydrophobic surface. Okay, surfaces. What it means that, and this one is the surface, the solid, and also the solid of the and also the vapor and solid of the in the liquid. Okay, so and I just now say that it's a outside. So it means that in that situation, the positive situation, the surface tension, the surface tension of solid between the solid and vapor interface is greater than the surface tension um between the solid and also the liquid interface, which means that the force is bigger than the this forces is bigger than this force to supply it. Yeah. Okay. So there's a question. What is the difference between gamma and SU? Okay. So these two situations, like, means that if you look at the force, okay, so someone asked a question, what is the difference of it? Okay. Here with the difference is that if you're looking at the gamma as a force, this the forces that needed to maintain the equilibrium for this one is bigger than this one. So we are these uh, uh, two different things now. Okay. Yeah. And also it's cost more energy if you have a bigger forces, it's more have the more energy and more forces to sustain the equipment. And another thing that you want to think about it, what is mean by hydrophilic surface and hydrophobic surface. And yeah, and we can further think about is like why is it forces is greater and this one than this one, and why is the energy is more for this one to this one. And you can think of the properties of the surface. We call it oh, wait, okay. We call it is hydrophobic. The surface that um don't like water. Okay, hydrophilic is what? The surface is like the water. It like the water. And the 41 is don't like the water. And if you going through this philic and hydrophobic and hydrophilic, and you think, I think you can get it why is it really the more forces for between the solid vapor interface uh, situation. Yeah, yeah, I did answer your question. Yeah, this is something to ponder, want to know why is forces. Oh, wait, it, you know, I look at it this way. I don't think it's about it for these two. Because if you think this one is the thing is positive, right? The left hand side of the equation is positive. So a thing minus a thing leads to positive. So A should be larger than B lah. Yeah, which is in this case, SV is not larger than S. Oh, you mean wait. Sorry. Okay, so I have to I okay. Yeah. This one because it's like interchange or simple, so it's a mistake lah. Okay, so yeah. Okay, thank you for correcting me. Sometimes I change the simple name, I change the bigger sign. So Okay, so and 4 minutes. What's this? Yeah, talking about the cap- cap- capillary action. Capillary action is in fact that in biology or in another sciences other than physics, you will find it, there's some application. So we said that is capillary action, like capillary action. Okay. So before that, we see on this thing, we want to define some things we call adhesive and cohesive, which means that this is adhesive and cohesive. Okay. Adhesive is some when the fluid, okay, uh, wait, think about this. Okay. For this situation, adhesive is bigger than cohesive. What does it mean? Adhesive is something when the uh liquid interface with the interact with the liquid. Liquid interact with the solid. Okay. So these are cohesive, and let's say we have the cohesive forces, cohesive forces, adhesive forces. Cohesive forces is that we have the inside for the liquid, between the liquid. Okay, inside liquid. Okay, let's say is the intermolecular forces is the cohesive forces that bind to each other, and let's say we have another forces called adhesive force. The liquid uh form some bond with the some attraction with the solid and also liquid. Okay, so there will be the and for this situation, which means that forces between the attraction of it is bigger than the this attraction between the molecules. Okay. So in another way now, if you see that is the in that situation cohesive forces is bigger than the adhesive forces. Okay, so it is another way now. Yeah, I will go through very fast. Okay. From young Laplace equation, like just now we are talking about young Laplace equation for two two radius. Let's say we have this surface, and we can find the uh, difference in the pressure. This one P is pressure, should be conversion should be bigger P lah. Just now we're using the bigger P. Okay. And use some of the we know that they have the question we have substitute. We consider a tube with two radius, like these two radius, let's say is a curve. Okay, so with this equation with delta P, difference in pressure equal to negative two two gamma over R. The negative is because of the is negative pressure added on in this impedance. Okay, and there will be other pressure which uh come from the another fluids that add on it, the fluid add on it. Okay, and we know that is the pressure is the H rho G. Okay, and this one we can integrate it. For this volume is we want to take this as hash or take this as hash, and we just neglect it. We assume it's very small. So and you read to the equation for this difference in pressure. You want to adding this one, sorry, adding this one with this one. Okay, here is the equation uh, for this called Green law. Another way around is from taking the work done. Work done is like you taking the consider the forces. Okay, so this time we consider it as a force over length. Okay, we consider it force over length. Okay, this one just now we using the dimensional analysis. We know that it's a force over length for or surface tension, right? So this one, it forces act on the length. What is the length? And we know that in that tube, we see from above point of view, we see that is the length, this total length, like let's say there's a point, we make it as many points, and many points on it is the you add on one forces, okay, surface tension force. Okay, so we want to total it up. The length is 2 pi r. Okay, let's say we want to change it. We use the work done concept. Let's say we change the initially it's a surface tension from here, we change it to here. Okay, with a delta h of the height of the change of the height. Okay, and this one is surface vapor tends to surface liquids tends to this forces is acting on the upside and the downside, and we know there's another forces is the pressure also. Okay, and relates to this equation equal to zero. Y equal to zero is an equilibrium situation, and we will derive at the same equation. Okay, this would be the Turing law and some capillary exchange. And this is this is trying to cooperate with the first law of thermodynamics. We are talking about fluid, and so because it's a conservation of energy, right? So we want to talking about we also we also talking about the conservation of energy in thermodynamics. We want to cooperate in, which is the first law of thermodynamics, and we want to study about the equation and found this equation. This one is we derived before. When you have didn't derive it before. Okay, this one will be the another idea of a kinetic theory. I think you guys studied about it before. Oh, okay, and previously we talking about the probability density function is this the it will be the PDF. I think I will take some 5 more minutes. Just at the end, we take 5 more minutes to think about it. The idea is that because it's a complicated equations, but you want to notice as have a unit of b minus 3 in the 3 dimension. Okay, because it's a 3 dimension, so it's a minus 3 power of 3 lah. Okay, power of minus 3, and we change our variable. Okay, this one is about the math thing. We want to talking about the maths. We call it Jacobian. Okay, some you want to let's say you want to have this ds dy dz Cartesian coordinate, right? Want to change to the other coordinate like spherical coordinate or cylindrical coordinate. You want to you derive it in the easier way. You can use a Jacobian, but then it's an extra stuff maybe you want to check out, but I will recommend you try to study other stuff first. If you have time, then you can go to a Jacobian, but it's a shortcut way. And I send the link also for the some you want to change your variable. Okay, from ds dy dz to another coordinate system. And this one actually you want to you treat it as a volume dv. Okay, and basically you treat the v as r. Okay, in the physics way. Okay, in the physics we can find a small dv through the physics. How is it? We swipe up this phi and swipe up this theta, and we know that this, let's say this length is dr. What is the sum from sum of the one coordinate xyz coordinate xyz. Okay, so this is dr, and this one is swiping some area of theta d theta. Okay, this length will be r theta, and this will be the So this one will be let's see from here. Okay, this is a data we're talking about from outside to outside, and we'll go the R side data, and we swipe some area, and you'll get a five D5. So swipe some area of D5. So swipe some, so you'll get the this length times the angle, so you get the this length. Okay, this length. So we treat it as a cube. So we simply multiply three together because when it's very small, right, it's somehow it's like a cube. So if you D or dv that we are talking about, so you are notice this why this weird stuff from here to here. This also a reason from physics way, and from maths way is objective. And I don't know if they're talking about this in the first uh we go to it. And yeah, this one when you're talking about this, right, this maybe you want to try to read this first. What is a flux? Flux. Okay, we're talking about it in before during in Penang camp, right? So today we talk about it also. So you can try to recall it back what is flux, and you want to study about it before you go to why this issue. Okay, a random works is come somehow is idea of the average is that they have a link inside between um, the average, like why we using root mean square instead of the um, mean of the things, and yeah, why we take this root mean square is like this thing square this and square root this for the random things. Yeah, this is why also you found that in mathematically, if you try this out, the mean value is will be the zero. So that's why you want to impose the root mean square into we are doing some random. We want to find the mean of the random things, random collection. Yeah, this will be the definition is a open or main. Anything you want to big. Efficient is things to notice is much smaller than the particular mean free path. It's something fluid is escape from that things. It's a small hole. Okay. The fluid is a fluid flowing out. It's something is about fusion that is, and this tube is much smaller than the mean free path of the particles. This will be efficient. Yeah. Okay. So I think cover the idea of. So, I will send the question that you can try for in the Discord. I think um recommended by them. Okay. So I think you must try it. Okay. Before we end, I just any questions? Yes. Okay. And also like if you have any feedback like because I'm quite new in teaching OFM, so things like you want to maybe you can suggest me to try to improve. You can test me also. You can put in the chat box, so if anything I can improve or if is it like very fast or very not clear or very the English is like not clear enough. Anything you can any feedback you can let me know. Okay. So want to try to change also. So try to improve. Okay, so okay, last one. Any questions? And Okay, I assume this question. So, uh, feel free to text me if you have any questions you want to discuss, any things you want to discuss also. The queries or any things you are not sure, you can ask me. So I will reply you my free time. So, doing some stuff also. Sorry if I didn't see the social media. And yeah, but then by the way, I didn't look at much on the Discord. So you want to discuss, I think better you use the WhatsApp. You can find it my from the WhatsApp group. Okay. So we discuss.